Hi guys, today we'll look at the Kaplan Meier model, which is also known as the product limit. So in the last session we were discussing about the types of censoring, where we looked at the type 1 censoring, type 2 censoring. We also discussed about the right and left censoring, the interval censoring, random censoring, informative censoring, and the non-informative censoring. So under each type of this censoring, you need to know the definitions of this, and you need to know which particular example is related to any of the censorings that we discussed. So today we'll be looking at the Kaplan-Meier model, and this is nothing but it's just a lifetime distribution, and it's just a step function with jumps at each observed death. And so here we're going to discuss how it's calculated with reference to the number and the timing of deaths and the number of lives alive at each point. So to get into this Kaplan-Meier model, we'll look at an example. So here we're going to use the Kaplan-Meier estimator to estimate a survival function or a survival curve. So here I'm going to go over that using this example, and this example has sample data of 10 observations. So the Kaplan-Meier estimate for doing an empirical estimate of the survival function R time t is equal to the product of xj less or equal to xt of 1 minus dj over yj. And here I'm going to define my xj as the distinct event times, or if you think of this as a survival versus death, you can say that this is just the distinct death times. So my xj is just nothing but distinct event, and my dj is going to be the number of death or event occurrences at time x of j, and then my yj is going to be equal to is just the follow-up times as least as big as xj. So basically at time xj, how many observations in your sample have survived at least up to that time or past that time. So here my t of I is just the follow-up time, and my follow-up time must be greater or equal to x of j. So we have this formula. So let's go ahead and get into estimating the survival function. So the first thing I'm going to do for my observations of 10 is that I'm going to order them. So if we order them, then we have what? We have 2, 2, then we have 3 plus. So this plus means that the observation is censored because it has a plus next to it. Then we have 5, 5 plus, then we have 7, 9, 2 16s, and 18 is the last observation, and it's censored. So I'm going to estimate the survival function, which changes at each time. So here I'm going to estimate the survival function at each time. Then I'm going to have my s of t is nothing but whatever values I'll get from my calculations. So the first time of event that occurs for my sample data is at time 2. So I'm going to estimate the survival curve at my s cap of 2, and this is just, and I'm going to plug this in the formulas. So I want O of x of j's which are less or equal to 2, then 1 minus dj over yj. So here in my observation of 10, 2 is my smallest event which occurs. So we only have to consider only 2 in our first formula. And then we see that we define our d of j as the number of events that occur at x of j. Exactly. So at time 2, exactly 2 events have occurred. So my dj will be, or it's going to be 1 minus 2 over y of j. And y of j is basically for the follow-up time that are greater or equal to 2. So all 10 of our observations is the smallest time which an event occurs, so all of our other observations or the follow-up time or the survival time is larger than 2. So all 10 observations, if you can see, are greater or equal to 2, which means that all 10 observations have lasted up to time 2. So our denominator is going to be 10. So for our S of 2, the estimated survival is going to be 1 minus 0.2. So this gives us 0.8, and we plug this 0.8 in our survival function. So the survival curve before our time t is less than 2, is less than 2, not equal to 2, is less than 2, is going to be 1 because no events have occurred prior to time 2. And when t is greater than or equal to 2, we have the estimated curve is going to be 0.8. So we are done with time 2. So at time 3, the observation is censored. So if we were to check this, the formula will be 1 minus. So since our time at t3 is censored, so the numerator will be 0 because no deaths or events have occurred at time 3 because this observation is just censored. So if we try to estimate the survival function at 3, this would just be 1 minus 0, which will give us 1. So we only estimate the survival curve at actual events of times, and we don't take into consideration observations that were censored only. So we're going to move past 3 and go to 5, and at 5 we have one event which has occurred and one censored observation. So here we're going to do the estimate of S of 5. So here we're going to just plug in because 2 is less than 5, so we have to take into consideration the previous events that have occurred. So this will be 1 minus dj over yj, and this is going to be 0.8 for x of j less or equal to 2. Then we also have to consider the observations at x of j is less or equal to 5. So this is going to be 0.8 times 1 minus the number of events that have occurred at t is equal to 5. So we have one observation and one censored observation. So that's just going to be 1 over all the follow-up times that were at least as big as 5. So it's going to be 2, 3, 4, 5, 6, 7. So our estimated survival function at S of 5 is going to be 0.8 times and 1 minus 1 over 7, which is approximately 0.857, and this is going to give us approximately 0.69. So we have 0.69 as part of our function. So this is going to be the value when t is greater or equal to t less than 5, and when t is greater or equal to 5, the survival function is going to be at 0.69. So we are done at observations at t is equal to 5. So the next time in event which occurs is at 7. So repeating the similar steps, so the survival function for t is equal to 7 is going to be the product of xj less or equal to 7, 1 minus dj over yj. So here we have to consider all the events that have occurred before 7. So less than 7, we're going to do 0.69 times 1 minus the events that have occurred at 7. So the events that have occurred at 7 is just 1. So it will just be 1 over all the follow-up times greater or equal to that point, which is 7. So 1, 2, 3, 4, 5. So we have 5 here. So we are going to have 0.69 by 1 minus 1 over 5. So this gives us 0.69 times 0.8, and this gives us about 0.55. So the estimated survival is going to be 0.069 between 5 less than or equal to t less than 7, and when our t is when our t is less or equal to 7, we're going to get 0.55. So our next event occurs at 9. So at this point we're just repeating the same process of s cap 9. So this is going to be 0.55 times 1 minus 1 over 4, and that gives us 0.41. So when our t is greater or equal to 9, what are we getting? We're getting 0.41. So we have two events which are occurring at 16. So that's going to be, so we get s cap 16 is nothing but 0.41, then 1 minus 2, because there are two events that are occurring at 16 and the remaining time is 3. So this gives us 0.14. So you plug it in. So when you plug this in, what do you get? So what do you get? So we have 0.14. So here we get 16, and then this is 16 less than or equal to t. So we have our last observation, which is 18 plus and is censored. So this is going to be true between 16 and less than 18. Since the last observation is censored, where we are not going to plug it in because we only plug in times where the death has occurred or an event has occurred to change the actual proportion. And for our t greater than 18, we can either do a tail correction and say that any value that's greater than the last value is going to go to 0, or sometimes people correct it and sometimes they use it to, and sometimes they use the t max, and it's going to continue up to 0.14 and it will never 0, or some people say that this value is never defined. Since this is a censored observation, So I am just going to say that this continues on to be 0.14. So now this is our final answer, and this is a discrete estimator of our survival function. And if you plot this estimated survival curve, you would get a discrete function. So you would get something like this. So you're going to have this. So you have got closed dots. So here you have got so this is a closed dot. So you have got closed dots on the left limits and open circles on the right hand limit, and this continues on up to infinity. So this kind of function is called a card lag function, or RCLL. So here we're done with this problem of estimating using the Kaplan-Meier estimate or estimator. So this is how we use the Kaplan-Meier model to estimate a data of 10 observations. So you can try out some questions in the material regarding the Kaplan-Meier estimate, and then the next time we'll look at the Nelson-Allen model. So thank you so much, and try to practice questions on the Kaplan-Meier estimate of the model.